When scientists discovered that if you look at something, it appears one way, but when you stop watching, does it remain the same? For instance, consider an apple on your table. As long as you're watching, it's clearly there. But when you turn away, is it still that definite apple, or does it transform into a blend of possibilities waiting for you to look again and decide its true form? It may sound like magic, but in quantum mechanics, it's no joke. In the microscopic world, particles behave in unpredictable ways. They act like waves, existing in multiple potential states until you measure them, at which point they collapse into a definite state, as if waiting for you to make a decision. This phenomenon isn't some form of telepathy. It's a concrete physical effect known as the observer effect, one of the most baffling aspects of modern physics. So, does our mere act of observation change reality? Or is there something more mysterious at work behind the scenes? To explore this question, we must revisit a classic experiment that revolutionized our understanding of the world, the double-slit experiment. If you're hearing about it for the first time, be prepared. It will upend everything you think you know about reality. And if you're already familiar, let's delve deeper to see just how mind-blowing it truly is. Here's what happens. Imagine a wall with two narrow slits and a screen on the other side that records what passes through. Now, take a handful of extremely small particles, say, electrons or photons, and fire them toward the slits. If these particles were tiny, solid bullets, you'd expect them to pass through one slit or the other, forming two distinct clusters on the screen. However, if they behave as waves, they will simultaneously pass through both slits and interfere with each other, creating an interference pattern of alternating bright and dark fringes on the screen. The puzzling part is that electrons indeed behave like particles when confined. They can be trapped, and you can measure their charge. Yet, when they pass through the slits unobserved, they suddenly act as waves, interfering with themselves. When we set up a detector to see which slit an electron goes through, something extraordinary happens. The electrons cease their wave-like behavior and instead choose a single, defined path, producing two neat clusters on the screen instead of an interference pattern. This isn't because electrons consciously choose a path. It's because they don't have a determined state until they are measured. In quantum mechanics, particles seem to exist as a superposition of many possibilities, and it is the act of measurement that forces them into one definite state. Now, what does this imply? Before measurement, particles don't have fixed positions or trajectories. They exist as probability waves, embodying multiple potential states simultaneously. It's only when we interact with them, when we observe them, that their wave function collapses into a single, definite outcome. Think of it as the universe rolling a die and choosing one number only when you look. This raises profound questions about the nature of reality. Does the world exist in a determined state if no one is there to observe it? Is reality, at its most fundamental level, nothing more than a shifting ocean of probabilities waiting to be resolved by measurement? For example, consider the age-old question: if a tree falls in a forest and no one hears it, does it make a sound? Quantum mechanics pushes this dilemma even further. Some interpretations, like the Copenhagen interpretation, suggest that particles remain in a superposition of states until observed, at which point their wave functions collapse into a definite state. Others, like the many worlds interpretation proposed by Hugh Everett, argue that every possible outcome occurs in separate, branching universes. There's also the pilot wave theory, which posits that particles always have definite positions, guided by hidden variables we can't directly observe. A common misconception is that our consciousness alone can shape reality, that our minds force the wave function to collapse. However, experiments have shown that it's not the observer's consciousness that matters, but the physical act of measurement itself. Whether a human, a machine, or even another particle interacts with the quantum system, that interaction is enough to determine the system's state. Imagine trying to pinpoint a ping-pong ball's location in a dark room. The only way to locate it is to shine a flashlight on it. Yet, in doing so, you might inadvertently nudge the ball. In the quantum realm, when we illuminate a particle with a measuring device, we inject energy into the system, disturbing it and forcing it to settle into a specific state. In classical physics, if you know an object's position and velocity, you can predict its future with precision. This is how we send rockets into space and forecast planetary motions. In the quantum world, however, the best we can do is assign probabilities to where a particle might be. This inherent randomness defies the deterministic view of classical science. Now, if particles only assume definite states when observed, does that mean reality itself remains indeterminate when unobserved? And if so, does the universe need a conscious observer to bring it into being? Some physicists propose that the universe might be constantly observing itself, particles and fields interacting and measuring one another, thus ensuring that reality, even when not observed by us, is still well defined. Alternatively, some argue that our current understanding of reality is incomplete. Perhaps our notion of measurement is simply a stand-in for a deeper process we haven't yet fully grasped. What is clear is that quantum mechanics forces us to reconsider our assumptions about what is truly real. To sum up, the double-slit experiment and the observer effect reveal that, on a quantum level, reality is not fixed until it is measured. Instead, particles exist in a state of superposition, a sea of probabilities, until an interaction forces them into a definite state. This discovery challenges not only our scientific understanding but also raises deep philosophical questions about the nature of existence. Is the reality we experience merely a projection of underlying probabilities? Could it be that our universe, in its most fundamental sense, only becomes real when observed? Perhaps, as some interpretations suggest, our reality is just a surface layer, a simplified version of a much more complex underlying structure that we are only beginning to comprehend. It might even be that the universe, much like a sophisticated computer simulation, is running on an intricate set of rules and hidden codes that we are only starting to decode. In any case, one thing is clear: quantum mechanics has shattered our classical notions of reality, leaving us with more questions than answers. And as we continue to explore these mysteries, we may yet discover that the universe is far stranger and far more wondrous than we ever imagined. Thank you for watching. If you enjoyed this exploration of quantum mysteries, please like, subscribe, and share your thoughts in the comments below.